I would appreciate if everyone, please, except for Grush, mute their microphones. It would be really great. So I can hear some noise now. If everyone can turn off their microphones, I think you'll have a better quality of presentation. Thank you. So I'll go through a few previous works I've done for energy harvesting, and then the main topic of today will be about random micro energy harvesting. I have established a new MEMS research group, Microelectromechanical Systems Research Group in Bath over the last 3 years. Our main objective is to develop new techniques for miniaturization of electronic and electromechanical systems. I put 3 main research projects here and our sponsors as well. On the top left, this schematic 3D microstructure shows microfluidic channels connected through magnetic microvalves on the top layer. There are embedded heaters underneath each magnetic component. We now investigate a new thermomagnetic method to switch the magnetization of valves and hence program the operation of this microfluidic channel. This will have plenty of lab-on-chip applications such as DNA sequencing and cell screening, as well as some mechanical RFID in harsh environments. At the middle, you could see a 3D schematic of a multi-beam energy harvester, piezoelectric energy harvester, that I'll talk in some more detail today about it. And on the top right, you could see the vibrotactile display pad that we have developed to help blind and visually impaired individuals receive the graphical information through the sense of touch. I have suggested and implemented a new resonance frequency-based actuation technique that increases the resolution in limited space without sacrificing any other performance criteria. So I have also listed the sponsors of my research in the Microsystems Research Lab, and also at the bottom right side, you can see the link to this group, which contain more detailed information about each of these multidisciplinary research works. So let's go to energy harvesting, please. So I have got some electronics background as well as my microelectromechanical research work. So in the past, I have investigated the interface electronics for micro energy harvesting. So I thought I can still have one slide about this topic as well, while it's relevant to energy harvesting. Interface electronics play an important role in the efficiency of energy harvesters, regardless of transduction mechanism, whether it is piezoelectric, magnetic, or wireless power transfer, which is the case in this slide. This is especially important when we deal with extremely small power levels. I had proposed a CMOS rectifier to improve the power transfer efficiency for implantable electronics. So you would normally expect the diode rectifier to improve diode rectifier in the top left to be implemented in CMOS technology, as shown at the top middle. So those are all CMOS transistors. That's what we would expect the diode rectifier to be implemented in a commercial CMOS process. This structure, the transistor-based structure, requires a threshold voltage to turn on the diodes. In CMOS technology, we could have very low threshold voltages. In the circuit at the top right, I have implemented a cross-connected rectifier in commercial 0.18 micrometer CMOS processes. It has reduced the total threshold voltage from 2 VTH to 1 VTH. And while we have this very low threshold voltage transistors, we could rectify voltages in the range of a couple of millivolts with this structure. So you can see the layout of this interface circuit and the dye microphotograph, which is in the middle bottom image. It shows a kind of experimental setup where I have put all the coils for wireless power transfer inside the port meat to measure the wireless power transfer efficiency, and I have compared it with the traditional, with the off-the-shelf Schottky diodes. So you can see that my circuit over there can increase the output voltage harvested through the wireless power transfer in the figure at the bottom left of this slide. This work was published in Engineering in Biomedicine in 2015. So I have started working on implantable electronics since then, when I found that the main challenge would be in the transducer side rather than the circuit side. So I would like to switch to my current work. So this work was where I was inspired to start working on implantable energy harvesters. So on the left side, you can see the implantable piezoelectric, the micro bellows, which were designed in 2014 to be implanted in the heart to supply the energy required for pacemakers. So the figure at the middle shows the schematic demonstration of how this piezoelectric material are integrated in various small dimensions to generate electrical energy from the heart muscle contractions. And on the right side, you can see the real life, the real world implementation of this microstructure. So although this has been a very fantastic contribution in the field, but because of the lower efficiency of these transducers, this hasn't been realized yet. So it hasn't been used in real world experiments. It has been trialed on animals, but not really for the human experiments. So the paper itself says that the energy harvested by this structure is about 10 times less than what is required for a pacemaker. So that was my inspiration to start how to improve the efficiency of microenergy harvesters. The 3D schematic you see on the left of this slide outlines the new technique that I have suggested for increasing the efficiency of microenergy harvesters using piezoelectric transducers. So here in this figure, you can see 4 beams, 4 piezoelectric cantilever beams, which are suspended from a substrate. So assuming that we can apply enough mechanical force to bend all these beams and let them resonate at their natural frequency, we will have 4 times higher output electrical energy, as shown on the figure on the right side of this slide. So we can just plug them and let them resonate at their own resonance frequency. But this doesn't essentially mean that we have increased the efficiency of our system. So no matter how much energy output, how much the increase in the energy output is, we have to spend more energy through the shuttle at the middle to bend the beams and let them resonate. So here in this microstructure, I'm trying to generate some mechanical input in micron dimensions using an electrothermal actuator that you can see. This is shown with a chevron-shaped actuator. So if you apply a low-frequency electrical signal to that chevron-shaped electrothermal actuator, it will move backward and forward, and it will plot the piezoelectric beams and let them resonate. But as I said, this doesn't mean that it will increase the efficiency of our transducer. There are some similar works in the literature. So for example, here, a group of researchers in Italy have presented this impact-based multi-beam piezo harvester. The red beam at the middle is where the mechanical impact is generated, and this impact is applied to the two green beams at the top and bottom of this bottom of this structure. This is a mesoscale structure, so it's quite large. And the resonance frequency of these two beams are at two different frequencies. So you can see the model for each of those two beams, where in combination they can generate a wider bandwidth and a higher energy output as well. So another good example in micro dimensions is a work presented by a group of researchers from Singapore. So this is in micro dimensions. So it's based on microfabrication processes. So you can see on the schematic image that on both sides we have a set of parallel beams. The one on the right is connected to a mass. So that is where the mechanical impact is generated. So that's our low frequency. That's their low frequency mechanical impact input. And then when it reaches in height, we can see a cross-section of this microstructure on the at the bottom of this image as well. When the mechanical input is applied through the mass, it moves at low frequency, but when it clocks the multi-beam resonance structure on the right, on the left side, it results in high frequency oscillations of the piezoelectric transducer. So if you look at the time domain signals, we obviously can see the low frequency and high frequency electrical voltage outputs. This is a deterministic environment. So still the efficiency increase is dependent on the nonlinearity introduced by nonlinearity and frequency bandwidth widening introduced by the clocking effect. So when the high frequency resonator is clocked by the low frequency mass, that clocking results in the frequency bandwidth widening, which is more obvious as it can be shown in this image at the bottom right side of this slide, where the increase in the mechanical input has shown the increased bandwidth, which is a demonstrator of nonlinearity introduced to this microstructure. So if we go back to this time domain multiplexing I've proposed in this work, to understand how this can be very effective in the random environment. So most of the mechanical inputs available in the nature has a random random behavior. So if we want to introduce how effective the time domain multiplexing can be for these random environments, I have suggested two scenarios here. So let's look at the multi-beam scenario A, where the two piezoelectric beams are both clocked by the mechanical input, which is represented here by the red line at the middle. That's just the shuttle. So it can introduce the mechanical input simultaneously to the both beams, both piezoelectric beams at the top and bottom. So in this scenario, if our mechanical input has a random distribution, then we can only extract the mechanical inputs, we can only capture the mechanical inputs that are large enough to bend the two beams together. So this means that we will lose most of our mechanical inputs that is shown on the distribution in the white area. So let's just repeat this. If we need enough force, such as F1, to bend each of the beams, then we will need 2 F1 to bend both beams and release them and let them oscillate. This much energy means that we will only capture the force inputs which are larger than F1. Let's compare this with a second scenario, which we can compare, plot those two beams in a sequential manner, so they are not clocked simultaneously. In this case, the total force that we need and at each time instant to plot them is equal to any of the beams. So it's equal to it's a smaller value. So just as shown on the Gaussian distribution at the left side of this scenario, on scenario B, you can see that a lower number of forces shown by the white area will be wasted in this case. So a larger number of forces showed by the dashed lines will be extracted. So that's the benefit of using this time domain multiplexing in a random environment. So if we go back to the microstructure that I showed in a few slides ago, I have made this scenario B and scenario A all together on the same chip here. So you can see my mechanical input here is generated by the electrothermal actuator at the middle, which is shown by an orange color. And the 4 beams are located and at unequal distances from the protrusions at the 2 sides of the beam. This means that 2 of the beams will be triggered, will be clocked sequentially, and 2 of them will be triggered simultaneously. So this will allow us, this microstructure will allow us to make a comparison on the same chip for the time domain multiplexing and the parallel beam scenarios. I have designed, and let's just look at the theory behind this thing a little bit. So the strain applied to each of these beams is shown here by the formula as zeta x, which is a function of the dimension of the cantilever beam. This is for a straight beam. So the output voltage of the piezoelectric beam exposed to that strain is also presented here by an integral form, in an integral form. So in this time domain multiplexing and in a random environment, if we define a function for successful mechanical inputs, in other words, the mechanical inputs that has been converted to electrical output, or they are strong enough to bend the beams and let the electrical energy extracted from the beam as n of t and f, then this can be a value of 1 for the forces that are strong enough to bend the beam, and 0 for the forces that are not successful. So the expected value of this function, of this new function, is also demonstrated in an integral form for the 2 cases when we have F1 and F2. If we go back to the the threshold level of forces that we needed to bend the beams. So for scenario A, when the beams are in parallel, if we need force F1 as enough force to bend it, then we have the time domain multiplexing. This force is reduced to F1 divided by N. So the output voltage of these two scenarios is calculated by the error function, which is the integral form of the expected value of the function that we defined for successful outcomes here. And it has been drawn in MATLAB for the different ratios and for the different number of beams that can be used in parallel. So you can see that when the number of beams increase, the expected value of output electrical voltage also increases, but within some limits. So it's not like that no matter how many beams we increase there, we add there, this will increase. This is all dependent on the properties of the randomly distributed mechanical input. But that shows that's a kind of theoretical proof for the successful results we measured by this time domain multiplexing method. So as a proof of concept, I have used a commercially available microfabrication process from MEMS-CAP. This is called Piezo MOMS. So it is simply an aluminum nitride piezoelectric layer sandwiched between a silicon thick layer at the bottom and a metal layer at the top. So you can see the beams are designed here in serpentine form. If you look at image A at the right side of this slide, so there is a chevron-shaped electrothermal actuator that can apply mechanical force downward and pluck the sharp tips of the free ends of the 4 piezoelectric beams. So a magnified image of the piezoelectric beams only is shown in figure B. These are the two right side beams which are designed to have different distances between their tips and the protrusion of the shuttle beam. So these distances are 5 micrometer and 10 micrometer. So another magnified image is also shown to is added to show the difference between the distances of the sharp tips of the shuttle protrusion and the beam's free ends. There were some microfabrication non-idealities, some faults in microfabrication that if you look at the sideways, the tilted image at the bottom left, you can see that the life wasn't as sweet as I was expecting. So the free ends of the beams were released at 2 different heights. So when I actuated my electrothermal actuator, it was missing the free end of the beam that I had there, the piezoelectric beam. So I had to take my device to our in-house clean rooms and deposit some further silicon dioxide at the bottom of the chip to make sure that it is thick enough not to miss the electrothermal actuator shuttle beam. So that was an extra thing that made this process so long. So it had taken quite around 2 years to get to this stage. And the dimensions of different parts are also shown there. So if we go to the experimental setup that I have used in my labs, so you can see here under the microscope we have a chip which is mounted on a PCB, and that is also mounted on a vibration isolation table. the electrothermal actuator is connected to a random generator, random signal generator that you can also see at the top of the microscope there. And the recording system consists of an oscilloscope and the vibration, the dynamic signal analyzer on the bottom right side of this image. So if I show you the video image here, so the video that I have recorded from the electrothermal actuator, it might help to better understand how it works. So you can see the electrothermal actuator is now generating some random band limited noise, not really a white noise, random band limited noise, and its tips are also touching the tips of the piezoelectric beams. So I'm just repeating the video here. So this is the chevron shape. I'm not sure if you can see my cursor at all or not, but you can see the small motions of the chevron, but you might not see the tip of the beam, which can which moves only in micrometer dimensions. So the results that we have recorded here, the simulation shows the simulation on the right side shows the resonance frequency of this piezoelectric cantilever beam, the S-shaped cantilever beam. It shows a 12 kilohertz resonance frequency, whereas when we measure the voltage output of this piezoelectric beam on the left side, you can see that's on 10 kilohertz. I assume this is just because of the microfabrication faults that I had to deposit further material. The deposition of that further material is not considered in the simulation. So that might be the reason for that 2 kilohertz difference in the resonance frequencies of the simulation and measured results. So we have measured the time domain signal from each of these cantilever beams. So in this image here, you can see 4 different voltage outputs from piezoelectric piezoelectric beams 1 to 4. So you can see, again, because of the microfabrication non-idealities, we have different amplitudes of voltages here. But when we combine these two and compare the two cases, when the two beams are excited together with the same random set of inputs, and compared it with the case where they are excited by time-multiplexed inputs, we have measured 4 dB volt RMS higher output voltage in the new time domain multiplexing technique. Thank you very much for your attention. I think I'm a little bit over my time. It was supposed to be a 20-minute presentation. So I'm ready for the questions if there are any.